Next group of students. Kalu. No.
Hello?
Hello.
Yeah, we're here. We're together next to each other.
Okay, so you next. Take over, please. Kalu, can we have your display?
Yes,
Kalu, are you having problem sharing your slide? No. Can you share your slide now?
Trying to share it via my laptop though. I'm using my phone to show my video and my voice.
You may not be able to do that with your phone. Okay. This will be the last presentation today. The wireless power transfer from Noor, Alawadh, and Kalu Hill.
Can you see my my slides?
No.
Mute you.
Kalu, don't share your phone screen. Just share your camera, not the phone screen.
Yes, Kalu, unmute yourself.
Can you see my screen now?
Yes. Yes.
Because in my phone I cannot see it here.
Yes, Dr. O, this is Mike Marcus. I see him, but not the screen.
We do not see your slides. We see you. No, we see you, but not your slides.
I'll share it again.
Noor,
if you go at the bottom where you mute your mic, it's gonna be a folder that has like an up arrow. You wanna click on that and then share the screen that you displaying.
I'm using my laptop to share the screen there.
Yeah, that should be fine.
Mm-hmm.
That works perfectly.
Yeah.
Loading up right now. But,
you guys see it now?
Oh, make sure you also mute your laptop.
It's on mute.
Mute like the other phone. Kalu's.
Do you guys see the screen or not?
Yes, okay. We see your PowerPoint slides now. Yeah.
Yeah.
Can start. Your slides are on.
All right. My partner in the project, Kalu, gonna start. So go ahead, Kalu.
Hello, are you there?
Yeah, just can't hear me?
Yes.
Okay. So, today just is me and is my partner.
You see you there. Hold the phone.
Yeah, me and is my partner is Noor. Noor, I'm Kalu Haile, and my partner is Noor. Just we're gonna present a wireless power transfer is WPTs, well widely known. So just as our advisor is Dr. O and Dr. Hagani. And today just we're gonna present introduction, the measurement, the availability of wireless power technology, the implementation, all is the block diagrams, the applications, the future work, and the conclusion. So the introduction part, so the wireless, just let me gonna define is a little bit is was wireless power transfer means. The wireless power transfer means transfer the electric energy from a power source to an electrical without any physical connection. So it can be used application where either instantaneous amount of continuous delivery of energy is needed. The conventional wireless system creates a mess when it comes to charging. It's different. It's devices like it's a phone, is any, it's a tablet, is anything we. So just we need to avoid is that thing we use the WPT. So is the worldwide just is known as three type of transmission. One is the inductive coupling power. Is the other one is a laser power transmission, and is a microwave, and is the RF is a power transmission. So today just is we are most focused on the microwave of RF is transmission. So the simple implementation of the power transmission power wirelessly used to be radio frequency and microwave power transmission protocol. So WPT is a technology. It can be transport power to location, which where conventional wireless is unaffordable, inconvenient, expensive, and is unwanted or impossible. Good. So now he gonna take is the measurement part.
So for the measurements, uh, up to now, do you have any questions though? Okay. For the measurements, we are looking for like worldwide how much people are transferring to the new technologies, to the wireless technology, because this technology is very old, as like the 1940s actually, since Nikola Tesla started doing 1840s or
1890.
And he started working for DC Motors for Edison. Then he went to produce an AC motors that everyone knows about it, the AC induction motors. It's very famous, very used widely, and now they are using it in the Tesla cars. Here we see in this chart that the mobile phones are going to the wireless charging, as you know, and you see every tablet, every actually every electronics nowadays, they are doing this small chips to implement in their devices. You can see the growth for devices are transferring to the wireless application. They are gone from almost zero at back 2012, back 2011, up to the 2020. Now they are so high at 1.5 million application. So going next to the next slide, we have here the demand and also the supply. Uh, this orange shows the overall growth of the whole technique, the whole technology. It's been at the peak since 2015, but there's no enough let me say, there's no large application nowadays for this technology applied for the consumers end of point. We aim here to show that since every application is going to the wireless, we have receivers. Then we have so many receivers. As you see, the growth of receivers are gone to the top, gone to the roof actually, and we need some transmitter to meet this supply, to meet this receiver kind of growth. And that's the focus for our that's another focus for our project, which is designing and transmitter and also a receiver, just to substitute the wires everywhere. So here's some calculations to show how scalable the project is. So we're now working on so much large scale in matters of providing power, electrical power, since the nowadays antennas, the protocol to transmit RF waves, the radio frequency waves, are not transmitting more than 15 volts. I'm talking about the commercially used nowadays, the small ones, the like Arduino, like so many transmitter around this day for power transmission. They have like 15 volts, up to 15 volts that's been accomplished, that's been achieved. For short range though, we are trying to have a long range of power, so we can power at least from building to another building, not just a few feet, not just like a few meters. So 1 gigawatt producing level means you are working at a power plant scale. 1 gigawatt. We're now working at that level though. We're trying. Japan have achieved up to 300 watts using this RF technology, this protocol, microwave protocol. We try to achieve some of that, but in order to do that, we had to order the stuff. Since COVID-19 came and the university is closed, we've been behind into doing that. So 1 gigawatts means in matters of electricity, I can power up to 110 millions LEDs. To produce such a power, we might need 3.123 millions photovoltaic panels to produce such a power. Equally, 412 utility scale wind turbines needs to be there instead of the solar panels. If you want to use the wind turbines as a power source, it will cost you 412 utility scale wind turbines, which equal 1.3 million horses to produce such a power, which means that that's very large scale. We're trying to achieve that, and actually the future work is to achieve that among having the communication with it. The new smart grids for the whole system has a communication with it to monitor, to keep it as a self-even healing grid. So we are not having any outbreaks. If gonna happen, we will know prior to the outbreak. We will know prior to the outage that it's gonna happen because of this type of this part of the grid, and we can isolate that part of the grid and still working on it till we maintaining it till it's back to work. Fun fact: such a power will need 2,000 Corvette Z06 to be produced. 9,019 Nissan Leaf. It's a very small hybrid car.
Oh, excuse me. Now we cannot see your screen anymore.
Oh.
I mean, we're looking at you, but not the PowerPoint slide.
Let
You
me
need
go
to
back
share
and check.
the slide. We can see your picture, your video, but not the slide.
It keep disconnecting for some reason. I don't know why. Do you see it now?
Not yet. You say no, it's starting to share content. It hasn't come through yet. Share screen.
Yeah. I'm having here your screen is being shared. So is this still shared?
No slide, no PowerPoint slide. You clicking on that icon from the left, 1, 2, 3. Yes? From your left, 1, 2, 3. The icon.
Yeah, it says allowed temporarily for some reason.
Oh.
When I'm
So,
open my slide, can you see it now?
no. No.
We will need to do it from here though. I can't see my screen here, but when I'm going to my slides, it's gone.
Hmm. You see your video, but not your slide.
How about now?
Yes. Okay, good. Yeah. Yes.
So why it's not on full screen though?
Measurements continued. You could not see your screen?
Yeah, I do see it.
Yes. Continue.
Okay, back to what I was saying. A fun fact: to produce such a power, the 1 gigawatt power, I say we need like what equivalent of 2,000 Corvette Z06, which is to a smaller scale the 9090 Nissan Leaf. It's a type of a hybrid car. Going to the available wireless power transfer technologies available nowadays, the inductive coupling power transmission, which is the most commercially used protocol. You can see them in every phone charger nowadays, and even in the toothbrushes, charging remote keys like the luxury cars. This will involve a conversion of electricity into high frequency. When we are transmitting the power in this protocol, in every protocol, we have to change the power form from DC or AC to whatever protocol that we are using. Here, they can use the high frequency alternate magnetic field. They're using for the transmitter and receiver. They're using coils. The receiver coil picks up the high frequency magnetic field and converts it back to the AC or DC power that's desired. The maximum efficiency of this system is achieved at its resonant frequency. There's a formula for it. The resonant frequency is determined by the capacitance and inductance of the tank circuit, meaning this is a resonant factor we have to calculate if we are using this protocol, and it's not going to give us that much of efficiency, and it's not going to give us a long range of power transfer. That's why we are not using this type of protocol. Moving on to the second protocol is the laser power transmission. Here, the most important thing is with the laser, we have the long distance achieved, but the power consumed and the power carried by the laser is not that much. It's not that efficient. But the photovoltaic in the same beam sometimes loses the power. Also, with the transmit power much to a longer distance, even several meters, this will be affected by the medium, because with this protocol, laser cannot go through every medium like solid mediums. The receiver, as I said, consists of a photovoltaic cells which are tuned to respond to the wavelength and the frequency of the transmitted laser. This wavelength and frequencies can be taken from the IEEE standards, but for us, we're not gonna use this protocol. We're gonna use the third one, which is the microwave power transmission. The reason why we are choosing this type is the complexity behind it, because for the senior projects, we need the complexity, as Dr. O and Dr. Mahmoud been telling us with our pointed advisor, Dr. Haggani. We need some complexity, so we try to use the microwave power transmission. We're gonna see later on the next slides how much complex could it be, and how much design behind this protocol. Unlike the resonant one, the inductive coupling one, it's a very easy kind of protocol to be achieved, and all you need the circuit for the technology to do it with the right coil to use. Here, a source of electromagnetic radiation is needed. We will need an RF, not RF, a frequency generator. To change when changing the AC power to RF, we need some kind of generator to send this to send it to the part of the transmitter. Sorry, a microwave receiver with a DC rectifier installed, meaning when we're transmitting the power, we will need a receiver. We faced a challenge here with this protocol, so we can send the power as low as we want, so for a longer distance that will keep the human beings are safe from any problem from the radiation. However, we will need to add a transformer with the receiver to step up the voltage whenever we need that. Same thing will happen if you are talking about a big large scale. We can use another transformer with the receiver to step down the voltage whenever we need, as a substation everywhere we need around the city or around the place we're trying to install this technology in. So moving on to the rubrics of the implementation, then I will get back to my partner. Here, the main focus is two things. The third one is included with the second, which is the when the end user getting the power. First, harnessing electrical energy. This wasn't the focus for our project, but we saw that if we are using a clean renewable resources of energy, that will give us a boost ahead for our a big actually convenience and even the environmental impact for our project. However, this project is not focusing on harnessing power. Any power source could be used. A desired input voltage will be modified as needed to be aligned with the whole aspect of our project. As I said, there's some transformer to control that. Also, we're gonna, for the future, we're gonna add more sensors like the PMUs, like the SCADA systems, so we can control our system to keep it self-isolating, self-healing, and all the standards that the IEEE follow for their grids, for the American grids, even the Canadian. Transfer electrical energy to other forms is the second rubric of this implementation, meaning we're gonna have the power source connected to our the transmitter. The transmitter will be a circuit that's designed with the modeled radio frequency to generate it and to transmit it through the chip, through all the components inside our circuit, especially the capacitor. I'll have to mention here the capacitor we trying to use, not right now, because of the COVID-19 we couldn't use it, is the graphene capacitor. It is we have three kinds of capacitor. I have to say this. We have three kinds of capacitors: the normal capacitors, the super capacitors, and the one we're trying to use, the new technology, is the graphene capacitor. It has the same space for the capacitors. However, they store more electrical energy in that space, more than the super capacitor and the regular capacitors. Also, this power inside the capacitor could be stored for more time, and also will be, I think, 5 or 3 times faster than the regular capacitor, which means you can charge your phone in a matter of seconds. You can charge your car, your electrical car, in matters of minutes instead of waiting hours and days in some situations. Getting back to my second rubric, the transfer electrical energy in other forms, we're gonna change from DC to AC. We don't have any problem converting the power from AC to DC and back. But why we are using the AC? It use more power, but however it is less to transfer and easier to transfer and more convenient to transfer. Even the power lines are using the AC now, and now even in the back. Sorry. Microprocessor or microcontrollers can be installed. And as I said before, we have a limitation here. We have a constraint of 15 volts, up to 15 volts. I couldn't see any microprocessors or microcontrollers that I could order right away that could handle more than 15 volts. So we went away to the semantics of how to get high performance transmitters and antennas. Uh, it was hard, but we could have accomplished more if we have more time, and if we could have some materials in our hands. But the budget was so low, and the time was not in our essence. So back to my partner Kalu, we'll talk about the block diagram of the whole system.
So as you saw in the graphic is a block diagram. Just we use the AC source. That is, I'm not saying that we are not using only the AC source. Just we can use AC or any kind of source. We can use the DC source. So as Noor mentioned, just we need is a little bit more complexity for our project. That's why we use the AC. So the AC sources, just we have to be make sure. Just where, as you see, this is we use a high frequency transformer. Just as once we generate the frequency, just we have to the AC source. Just is see the AC source here. Just is gonna transfer power for the. Just show them. So the AC source is gonna transfer the power from for for the resistors. So that's resistors, and we're gonna use is a full bridge, a full bridge, a full bridge, a full bridge is bias transfer. So that is that one. Just we have we make sure that is we are not gonna lose this too much power. So when it transfer is this one, it must be much. The one you use is our project is we don't order is the high frequency, just is instead of that one we used is a coil. The one we transfer the coil, it must be much is the transfer coil, and it's the receiving coil is a frequency, it must be much. Otherwise, is the transfer thing is not occur. So yes, we working hard for the project that we got is the same kind of its frequency. So after we send it the frequency, that one just we're gonna transfer it to the rectifying. Rectifying is that one rectifying. Rectifying just we're gonna if we have is the AC source, just we have to transfer it with DC source. So after we rectifying it directly, we're gonna transfer for is our output. So our output is we uses our thing for DC fan. Just is
That's
so
just to
that
show the load.
just only for to show a load. That we can use any kind of thing for is as a load. So
Appliances, charging phone, charging gadgets.
yeah, so we use is a DC fan. So Noor, you gonna go ahead now? No.
Going in depth, Hi everyone. Going in depth for the transmitter, which is the most important thing here. I have a nice diagram here, the nice block diagram here to show for the transmitter. Let me explain what's a transmitter. I should have said that earlier, but this is the part where I mention it. In electronics and telecommunications, a transmitter or a radio transmitter is an electronic device which produces radio waves with an antenna. Let me say that again. Electronics and telecommunication, meaning this radio frequency can be used for transmitting power in electronics, or transmitting for radios or for televisions as telecommunication, or even for phones. Because in one paper that I read, using this high radio frequency that we might go up to 1,000 gigawatt, gigahertz, that will open so many channels. These channels could be used for communication, as like the Zigbee and also the Wi-Fi, the 2.4, 2.5 gigahertz. These might be used as communication channels. However, we're trying to implement the 5G network as controlling everything for our project, though. Going back to the transmitter itself generates a radio frequency, alternating current. So I have to have AC power to AC current to transmit that, which apply to the antenna. When excited by this alternating current, the antenna radiates radio waves. Now I have a carrier. I have established a carrier for my signal. The transmitter is where we apply the electrical energy to transmit. Our message will be the electrical power. Could be AM transmitted, could be so many kind of transmission could be used. We're using high frequency. However, as I mentioned before, if I go up with the high frequencies, then I'll have an issues with the human consumptions of radiations. So we're gonna use transformers as needed. If it gets to hurting human beings, we're gonna use transformer to step up or step down the voltage, so we can use lesser frequencies. The transmitted energy may be in the form of light or changing magnetic field. This talking about the inductive coupling way, and the other way with the laser one, or the electronic wave like microwave. That this is the one that we're using. This is the diagram. As I said, we need a radio frequency source, a radio frequency generator to have this high frequency. Then I'll have a matching network. The matching network basically could be a filter, a low pass filter, a high pass filter. There's so many kind of filters that could be used as desired. This these aspects, these factors, I'm saying in a general way, that these could be specified to your desire, to the consumption end of user desire. Then I'll have the transmitter, the TX antenna. I don't need a rectifier here. I might need a converter from AC to DC before the RF source. That would be that would be as needed, though. Now let me go to the medium and receiver, which is I have sent the signal. I have sent my message on top of that signal. Where is it going through? The medium is where the transmitted energy is passing through. The medium can be solid or vacuum or air. That's the where the convenience and efficiency of micro power transmission come the microwave power transmission come. Sorry, the medium can be solid or vacuum or air. Meaning, here this is one of the advantages. This is one of the pros that our protocol our project introduce. It can go through mediums like buildings, just like your radio. Think about the radio. Do you need to have your antenna in the air to get the radio, or can you use your antenna inside your house to get the radio frequency you want to listen to? So continuing to the receiver, since we don't have any problem with the medium, it might have some less of efficiency, some effects on the efficiency. It's not that big of effect. Doesn't need to be mentioned, though. Moving on to the receiver is the one which receives the transmitted power. Now, if you look at the bottom left diagram, you will know what I'm saying. It will have some meaning. I have my power transmitted through air, through the medium. Now I have the receiver. Here where we most face the challenge, the receiver. Since I'm telling you I cannot have more than 15 volts, then I will need a specified the transmitter and receiver to get that power. Japan already got up to 300 watts, and also NASA is working on it. Also, General Electric, they are promising to have more than 10K watts transfer wirelessly through their appliances, through their technology, which they are using the same technology we are introducing today. We will have the power coming to the receiver. Then the receiver, how could it know which kind of signal to only get? By the matching frequency. Then I will have a rectifier. I will need a rectifier because this antenna could be called a rectenna. An antenna and the rectifier itself coming together, because I will need to change the signal that I'm sending back to DC, back or to AC for me, in order for me to use it. Then a storage could be only the capacitor that I'm talking about, the graphene capacitor, so you can use this technology right away, or you could attach it to a load, just like I'm saying, the transformer, to step up or step down the voltage. Any questions? Okay. Going to the requirements and constraints, I'll give it back to my partner. Go ahead, Kalu.
Hello?
Okay, just can you hear me?
Yes.
Okay. So the requirement and the constraint, so we are working for is the RF. So most of the things that we are using is a microwave wave or the radio frequency. So the other waveguide for a guiding wave particular direction. So this means that is it gone to the air. So that is without to lose this too many power. So it gonna gone is one direction.
If you don't mind, let me show you just a picture.
So Noor is here. Hold on. He will show you one picture if you can see it. Just can you see it?
Can you see the picture that I'm showing?
No, we don't see the screen with the picture. Where
Do you
you
see-
need to share screen, and if it's big,
not the screen. Look at my camera. Do you see the waves, how they're moving?
yes.
This is what happened to the antenna, the sending the power. So the guide, it will send the power directly to the receiver, saying, meaning we will only have this part showing. Can you see? Can you see the cursor? Only this part showing to send the power to the receiver. Then the receiver should get it as the guide signal will be in both antenna receiver and the transmitter. So back. Can you see the slide now?
Just can you see the slide?
Yes.
Okay, go ahead.
Okay. So the other one is a microwave power antenna. Just as you mentioned, we can use different kind of antenna. Just in a market. We got some kind of antennas. That one is the micro strips, and the parabolic reflector, and the other one is slot wave guiding antenna. So this is a receiver, as Noor mentioned. So all the receiver part that is as we call it as a rectifier we call it is a rectina. Explain the efficiency.
Now going to the efficiency. It's a part of the requirements and constraint actually, since we want to achieve as much as possible of the power law, of the power efficiency, of the power transfer efficiency. The highest microwave to DC electrical energy conversion achieved was 84% in an experiment back in 1975. If you see, this technology is very old, it's not very new, but however it's not been implemented for the end user, for the consumption of everyone that can have access to. More practical system with the higher power output have had lower efficiencies, as I mentioned. To solve this issue, a transformer can be added to step up the voltage to get the desired output, as I mentioned before. A team in Japan built a system consisting of a set of solar panels attached to a microwave transmitter and receiver. This system was able to achieve conversion efficiency of over 75% with an output of 300 watts. 300 watts that can actually power up many stuff. Actually, can even power up appliances and also the small gadgets. Small gadgets I can work in up to 1 watt, 1 watt to which means 5 volts up to 18 volts. With our project, we were aiming to achieve 95% efficiency with using the slotted waveguide antenna. There's some technique with the symmetric of antenna that we could play with the frequency and with the electronics, the power electronics used inside this our circuit to achieve this 95% of efficiency. However, we couldn't have any simulations for that because we didn't have the parts, we didn't have we couldn't design a receiver that can get more power. When I'm saying designing a receiver, a small receiver like an antenna, we don't want to have a large inconvenient stuff, electronics to apply for the users, because they're gonna see it as inconvenience and also hazard for them to use, because it's gonna have all this radiation received even with the guided signal. So moving on to the safety, is it safe for humans? I could jump to conclusion and tell you that there's not been any case documented for anyone been harmed by our protocol we are using. So first, safety of wireless power transmission depends on how powerful your transmission is and what protocol you use. Our protocol seems seem that it is so harming to the human being since it's dealing with radiation, but actually it can pass it through humans like a free space. Second, commercial products like wireless smartphone charger are very much safe to use and pass several safety tests before arriving at market. As I showed you earlier, there's so many commercial products for phones and tablets and even appliances that are going with the wireless technology. So there's no any harm in that. We are not transmitting electricity through the air like Tesla coil. Like, you're not gonna find any lighting going through the air. It's only the RF power transmitted. So it's just like the radio frequencies you see around. Do you see them? Can you feel them? Little bit, yeah. With the inductive charges are safe, and it won't shock you if you place your fingers between the transmitter and the receiver coil. So there's some applications for the inductive for a hybrid system, having wirelessly transmitted the power to your house using a microwave, then using the inductive coupling way to have your power transmitted inside the house, which make a more controller, and you can apply the PMUs, the SCADA that I've been talking about, the per unit measurements, and the SCADA system to monitor and to control the power using the inductive hybrid way of a protocol. The microwave power transmission is several decades old concept. However, till now, there is no documented health hazard due to wireless energy transmission. So with the full mouth, I could say it should be safe unless you are using a high power to transmit with a high frequency. And I said earlier, to avoid that, we could use a transformer whenever we want to step up or step down the voltage. Moving on to the application, I'll transfer you to my partner Kalu.
So what's the benefit of WPT? So the first is the WPT system completely reduces existence high tension power transmission cable substance of tower between the customer and the generating station. This is in the house, just we see too many wires in one place. So if we use this technology, so we're gonna garbage all the wire and we're gonna transfer the power smoothly. And just is so the cost is the other one is the cost. Is the cost is just we see too many researches. The cost is almost is a well less is the one we use it right now. It comes with in a wire, so we can use the radiuses by 50 up to 75% is less.
To add to my friend, here we don't have any heat. We have less heat transmitted, and actually to use the power lines, excuse me, to use the power line, it costs $10 billion to use the regular power lines, the wires, to distribute the power. Imagine if you are having this $10 billion in another used in another searches in another field, because here you're not gonna have any wires installed. Actually, the antennas around the globe could be used already. So you're only gonna install your technology on top of these antennas already around the world, already exist around the world. So the cost will be less. The electro energy consumed or been lost by transmission will be less. The power could be transmitted to places to which the wire cannot go, um, cannot reach, like urban areas. Like let's say if you wanna power something that moving easily with this protocol, but with wires, it's not that easy. Actually, it's kind of impossible. So moving on, the largest application of the wireless power transfer is the production of power by placing satellites with the giant solar arrays. It has already been researched and been tried by Japan. Uh, this system could actually give us a lot of benefits for the environment, for the social, actually, because it saves so much space, it saves so much you're not gonna deal with the because when you are installing turbines, you are dealing with the you are dealing with the heat with the heat, and also, sorry, not the heat, you are dealing with the shades of the turbines, because you cannot use these also areas, uh, the shade area, in plants, or even in installing another stuff, another electronics. So the solar power system, the satellite power system is very good application here. The wireless power transfer is used in moving targets, like just I said before, if fuel-free electric vehicles, fuel-free appliances, fuel-free rackets, and moving robots. The most important word, the keywords here, fuel-free. We're not using fuel, not fossil fuel, not uranium, not nuclear power. I mean, not any kind of fuel. You are using only electricity changing from form to another form. That's it. The other application of wireless power transform is wireless power source. Having a wireless power source everywhere you want. Like if you have an emergency somewhere, military emergencies, they need some power, or they need some even communication, because just I said, with this technology, you are opening, I think, 16 channels of variant channels. One of them is the communication channels. Could be working in any frequency, because we are using frequency as high as let's say 900 megahertz up to 1,000 gigahertz. That opens a lot of channels. Could be controlled, could be monitored, could be even communication between the transmitter and receiver. So there is so many applications cannot be counted as 1, 2, 3. There's so many applications. So let me move on, because I'm kind of getting a lot of idea coming to my head. But let me move on to the other slide. This is one of the application could be done, is the powering electrical trucks, having stations to power these trucks from the top. This is just one way form. We have another way. We have another way is, and you can see here how much power is needed to power this truck. We need more than 5 kilowatts to power this truck. Actually, the 5 kilowatts even can power a house. So if I can transmit this kind of power, upper than 5 kilowatts, I could power up houses, because the normal houses in the United States nowadays, they use an average between 5 to 7 kilowatts. The other way is to have the transmitter in the bottom of the road, like in the filter itself. We can add a transmitter, and the receiver will be in the cars or in the moving vehicles. Any moving vehicles, like here, you're gonna see a moving vehicles moving. We are trying to the researcher try to emulate the moving vehicle with the road itself by a transmitter down there. We're not using coils though. We are using a microwave. Don't forget, we're using a microwave type of protocol. We're using high frequencies from 900 megahertz up to 1,000 gigahertz. Any question? Okay. I think now we have showed everything from what's a wireless power transfer, how could you apply this technology, what kind of application is there. Going to the future work for us, as I said, we're trying to integrate the 5G network, which can provide the communication option to the system. As the power demand grow every day, electronics need to be as functional as possible. So I need to monitor them and control them, and as energy efficient as we can make them, to keep the power consumption at its minimum. Because everyone talking about every engineers, every management for the power plants, they're talking about the peak demands, when they are happening, how I can meet the demand of the power. With the wireless, with all the features that we are trying to introduce in this project, which the self-healing, the self-isolating, everything in this project shows that you can control them more, and also you can automate everything, just like the Internet of Things. Just like how can you control your LED with the Internet of Things? How can you control your doors, your irrigation system with single buttons, with single alerts? Could you know which issue you're gonna have in your grid, and which can also provide suggestions due to what can be solved for this issue. Also, if you're gonna use batteries to Tesla company nowadays using farm storages with batteries, like they are putting batteries as a farm to keep this power. But with our technology, it's just to keep the power moving around between transistor to another receiver. That would be enough. You don't need any storage. But if you want to, there's so many new type of storage batteries nowadays, not using lithium. There are even batteries that are reproducing the power itself. This could be this might be mentioned in the final report, but just for future work, summarizing future work of us, we are only trying to put because we have full understanding now of the concept of wireless power transmission. Now we can build a smarter grid that's using only wireless power transmission. We're not using any wires anywhere. Wireless power smart grid has a chance to change the way we use our electronics and to become a very useful tool. That's what we're trying to use. That's what we're trying to introduce today. So to conclude, wireless power transmission would have many interesting applications. Some of the applications involve simply powering devices, which is very important, which is the high demand in, or vehicles, like everyone now talking about the emissions and the global warming and the cause that contribute to it. Actually, one of our classmates, Victor and Kairi and Ivan, they work on to electric motors. This technology could help them by powering their electrical motor without a motorcycle without using a battery. I have heard them earlier and even before they're talking about the battery, and they couldn't buy a battery because of a high price. With this wireless power transfer, you don't need a battery. If you hear me, Victor and Kay and Ivan. So continuing from a remote power source, this is the essential key here. It's a remote power source. I don't need a battery. It's not gonna explode. Nothing here. Even the hazard is becoming less and less going through the project. High efficiency wireless power transmission is possible. As I showed you, there is achieved up to 87 now or 85 achieved percent, and we are working in the 95%. I think this is like
more beyond we
yeah.
expected.
I think we are making the impossible possible here. If we just have more time to implement our project. Continuing, the energy grid could be affected as well if long distance, high efficiency wireless power transmission is possible. We could reduce our reliance on transmission lines. That's the most important thing, actually, to get rid of every wire that we are using nowadays. To transfer energy over long distances. Moreover, wireless power transfer could allow an alternative source of clean energy. This is another key, by transmitting solar power from space back down to places where it is needed on Earth. Further research into wireless transmission will show whether some of these plans are feasible. Thank you, everyone. And if you have any question, please ask away. Me and my partner here are ready to answer them. You get the mic, Dr. Off.
Yeah, any question for the group, this group? Do we have any question in the chat box for you? Loud and clear. No question in the chat box. No.
Thank you.
So, are there any questions for Noor and Kalu?
I think we did a good job. No one is asking.
Well, I want to thank